Assalamualaikum warahmatullahi wabarakatuh. My name is Naila Darin Anindya with student number 220-682-9585, and in this video I will be explaining my answer on the first question of student version military applications of spring mass systems problem. So before we can continue to the question and answer, I will explain a brief explanation on the thinking process that I will be using in this video to solve the problem. So I will be using the W5 conscious thinking process, which reminds me to always stay conscious and that what you do is for God, which is the intention. Then you can continue to the initialization and idealization and instruction to solve the problem. So the first question is, we are told to model the suspension system of an STT trailer while it is loaded with a satellite using these three different shocks, which are the air coasters, cloud riders, and extreme shocks. The trailer of an STT at rest will be loaded with a satellite with a mass of 1800 kilograms. Assuming that the loaded trailer is at equilibrium, the displacement of the shocks before the trailer is loaded is 3 centimeters. So there are three objectives here. The first one is we gotta determine the critically damped value for each shock, an example the optimal value, to avoid oscillatory motion, and then compare the damping coefficients of each shock to its critically damped value. The second objective is to solve the spring mass system for each shock with the given damping value and also with the critically damped value. For each shock, plot the solution with the given damping value and the solution with the critically damped value together. And the last objective is to discuss the model of each shock with regard to the satellite being placed on the trailer. From your analysis, decide which shock is best for the STT suspension system for loading. So basically, the main objective of the first question is to decide which shock between the air coasters, cloud riders, and extreme shocks is the most suitable to be used for the trailer trucks. So, first is to know what the objective is, and as I said before, our goal is to analyze the behavior of the STD trailer suspension system with three different shocks during satellite loading, and we want to find the optimal shock, which is critically damped, and compare its performance to the given shocks. Finally, we will choose the best shock for the loading process based on the analysis. So on to initialization, we need to consider what's known and what's unknown. So what we know is the mass of satellite, which is 1800 kilograms, and the initial displacement of shocks is 0.03 meters, and the spring constants K and damping coefficient C are shown in the table as I showed before. This is the table. And what we don't know is the critically damped damping coefficient for each shock. So on to the solution idealization, which is the method that we will be using. So the first step is to model the system. We will model the suspension system as a single degree of freedom spring mass damper system. The satellite mass represents the sprung mass, and the trailer itself acts as a spring and damper. Then we will utilize the formula for the critically damped damping coefficient for a spring mass damper system, and then we can compare by solving the differential equation governing system motion for each shock's given damping coefficient and the critically damped value. We will then plot the solutions together to compare their behavior. So for objective A, we have to calculate the critically damped damping coefficient for each shock using the formula C critical equals 2 times square root K times M. So after we calculated the C critical values, we have for the air coasters 1540.6 newton seconds per meter, and for the cloud riders is at 382.8 newton seconds per meter, and the extreme shocks are at 1224.7 newton seconds per meter. Then for objective B, which is solving the spring mass system. We can now solve the differential equation for each shock using the known mass and the provided or critically damped damping coefficients. The general equation for the displacement in a damped spring mass system is as shown here, and then we can solve this equation numerically using software like Python. The solutions for each shock with its dampened damping and critically damped value can then be plotted together to be compared. So here is actually the Python code to find the value that we're supposed to calculate. From the plots calculated in Python, we can observe the behavior of each shock suspension system during satellite loading. The critically damped system will reach equilibrium the fastest without any oscillations. Shocks with damping coefficients closer to the critical value will also exhibit faster settling with minimal oscillations. So since we gotta use Python first, but here is actually a preliminary analysis recap. So for the air coasters, its damping coefficient is far from its critical value. So this will likely exhibit significant oscillations. And for cloud riders with a damping coefficient much higher than its critical value, this is also not a good choice because it might be overdamped. And the last one is extreme shocks, which has a damping coefficient of 1110 newton seconds per meter, which is closer to its critical value, and this is expected to settle quickly with minimal oscillations. So from all three analyses, we can now decide which shock is best. So based on the analysis, extreme shocks seem to be the most suitable for the STT suspension system during satellite loading, as it approaches the critically damped behavior closely, so it will ensure quick settling with minimal oscillations, thus minimizing potential damage to the satellite.